So let's take out our flow chart again. We've already done the first step. The first step was, hey, do we have a GCF? Yes, I follow that, and it says factor the thing out, or no, then both of these, whatever the ultimate answer, they lead to the next question. So what is the next thing that I'm supposed to determine when I'm going to factor a polynomial? So after factoring out the GCF, it says, how many terms does it have? What's the number of terms that your polynomial has? So we have three choices here. We got 2, we've got 3 terms, or we've got 4 or more terms. 2 terms, it's a binomial, 3 trinomial, or 4 or more terms. Each of these cases, we're going to do something different. So we're going to take the left-hand side of that diagram. We're going to start with 2 terms. That's what we're going to do next. So we're going to factor some binomials. That's what our next objective is. Objective 2, you're going to be able to factor a binomial. So binomial has 2 terms, and so you can see in this piece of artwork, of course there are 2 squares here, and those 2 squares are slightly different, right? They differ by some color, but they're still squares. And you're going to see in just a second, the very first way that I'm going to factor these things is using the pattern for the difference of 2 squares. And, well, both of these binomial factoring, both of these processes have to do with just following patterns. Okay, so if we know the patterns, it's going to be a piece of cake to factor these things. Okay, so the first one is the difference of 2 squares. And we've seen this before whenever we were multiplying polynomials. It looks something like this. I had x plus 3 times x minus 3, let's say. So whenever you go to FOIL that out, the middle term cancels out, and I'm left with, see, there they are. I'd have a negative 3x and a positive 3x. They would cancel out, and I'd be left with x squared minus 9. And we call this thing the difference of 2 squares because x squared is a perfect square, and 9 is a perfect square. It's the difference of those 2 squares. So remember what factoring is taking that x squared minus 9 and working it backwards to try to come up with x plus 3 and x minus 3. So that's what we're trying to do here. I'm working this thing backwards. I start with the difference of 2 squares, x squared minus 9, and I know the pattern for that is going to be x plus 3 and x minus 3. How do I get the 2 things that are inside the parentheses? Look at the numbers there. What's the association with them? Well, that x squared minus 9, again, the difference of 2 squares, if I look over there in the factors, x in both of the positions, x is just the square root of the first term, x squared. The 3 is just the square root of the 9. Okay? So they both look the same, the factors look the same, but one's positive and one's negative, and that's what makes the middle term cancel out. Okay? So let's try this. Well, again, if you need to write something down, there it is, but it is on your flow chart, difference of 2 squares. That's the first one that we're going to do. How about the difference or the sum of 2 squares? So the sum of 2 squares instead would be like this. It would be x squared plus 9 instead. And the answer to that one is that there isn't one. So if it's the difference of 2 squares, we can factor it. If it's the sum of 2 squares, it's prime, and you cannot factor it. Can't factor with real numbers. You can factor it with imaginary ones. Anyway, so let's go ahead and factor a couple of these difference of 2 squares together and then get yourself some practice on it. All right, so I'm going to notice that the first one is the difference of 2 squares. Well, actually, remember, that's not the first step. The first step is GCF. Do they have something in common? Well, they have a 1 in common, but that's not going to help us factor this any, so I'm going to say, no, I'm not going to factor out a GCF. Now I'm going to look at both of these terms, and I'm going to see, hey, there's a minus sign in between it. Okay, I'm good. And then, is this thing a perfect square? And is that one a perfect square? The answer is yes, because the square root of 16x squared is 4x. And the square root of 1 is 1. So I'm just going to go 4x plus 1 times 4x minus 1. Difference of 2 squares. Done. Okay? Now, number 2 is a little trickier. It's a little bit trickier. Look at this. It has to the 4th power. But the 4th power is also a perfect square, because the perfect square is x squared squared. If I were to square x squared, I would get, remember you multiply those powers, I would get x to the 4th. So it is a perfect square. So I'm going to write this one as, again, the square root of 16x to the fourth should be 16x squared plus 1, not 16. No, not 16. That should be a 4. Silly, silly. 4x squared plus 1, and then 4x squared minus 1. Okay, we're done, right? Actually, no. Let's go back to number 1. If I go back to number 1, there's not a single thing you can do to further simplify each one of these. There's no GCF, no difference of two squares left or whatever, so it's completely factored. Okay? Down in number 2 here, a 4x squared plus 1 is the sum of two squares, and you can't do anything with it. But in the second set of parentheses, that is 4x squared minus 1. That's the difference of two squares again, so you can keep going on that second factor. So if I'm going to completely factor this, the first one stays the same, 4x squared plus 1. But the second one factors as, you take the square root of both of these, 2x plus 1 and 2x minus 1. Now it is completely factored. Because the 2x plus 1 and the 2x minus 1, you can't do anything further with it. Okay, number 3. If I look at both of these, they are perfect squares because 9 is and 4 is. The problem is that this negative sign is right out front. It's supposed to be in the middle, isn't it? That's okay. Let's just fix it. Let's just write it as 4y squared minus 9x squared. Now it looks like the difference of two squares, and we can factor it. So take the square root of both of these things. It is 2y plus 3y, and then the same thing with minus. 2y minus 3. It's not a y, it's x. Fix it. There we go. 2y plus 3x and 2y minus 3x. There we go. And now both of those are prime, and it is completely factored. So why don't you give it a shot here on these 3 problems. Try to factor those by difference of two squares. Again, let's check our work. Voila. Okay, so I threw a couple of curveballs at you. Number 1 had decimals in it, but each one of those decimals were perfect squares. So 0.25, the square root of that is 0.5. And same thing with 0.49, the square root of that is 0.7. Okay, so it was factorable by difference of two squares. Number 2, you did have to pull out a greatest common factor first before you could factor it as a difference of two squares. So what was common to both of them is 3x. And when you pull it out, you're left with a quotient of 9x squared minus 4y squared. And that's a difference of two squares. So then you can factor it as 3x plus 2y and 3x minus 2y. And don't forget to keep your 3x as one of the factors. All right, and number 3 might have been tricky just because I threw a fraction in there. But the fraction itself was a perfect square. If I have 9 over 25, take the square root of the top and take the square root of the bottom separately, I got 3 over 5. So it's the difference of two squares, 2m plus 3/5 and 2m minus 3/5. Okay, so there's still a little bit more work to be done on the binomials. So the next video is going to check out cubes.